Hello, everyone. So in this video, I want to discuss the measurement handout. So if you could follow along with the measurement handout, that'd be great. So this is going to discuss some ideas on graphing, like what's required for a good graph. I'll talk a little bit about slope, review that concept of slope. And then we'll talk, I guess the more important part of this handout is how to measure accuracy and precision. So we'll be computing two measures, something called the percent experimental error and percent experimental accuracy to measure accuracy and precision. Okay, so let's begin with this first page. So I have a graph here, but this is an example of a poorly drawn graph. Why? What's wrong with this graph? Now you may recognize here, well, there's not really labels, right? You see F and A, but what does that mean? Like maybe this is force, maybe this is acceleration. So you want to make sure you have good labels for each of the axes. Along with labels, you need to have units, right? So what are the units of force? Maybe newtons, maybe pounds, right? So you want to make sure you have units. And the same thing for the y-axis here, acceleration. Let's say it's meters per second squared. What else? Well, in addition to labels with units, you want to have a title, right? Sometimes the title's on top, sometimes it's on the bottom. Actually, when we do these graphs on the computer, we'll find that the title gets printed out on the bottom left-hand corner here. But you need some sort of title. And the easiest title to give a graph, if you can't think of a good name, is simply give it the Y label. This is called the dependent variable versus the X label, which is the independent variable. So if this were acceleration and this is force, you could call this graph acceleration versus force, right? It's always Y versus X, and then that would be fine. Now, another thing, and this will come up quite often throughout our labs this semester. Here's my data, right? So each of these represents a data point. And in this particular graph, everything is connected by line segments, right? Each pair of points is connected by a line segment. That's maybe not the best way to represent this information, because if we're trying to show a relationship between this variable, say acceleration and force, and here's our plot, probably by connecting it with line segments isn't the best way to show that relationship. Better would be a curve of best fit, right? Some curve, some smooth curve that goes through all the data points. In this case, it looks pretty linear. So you'd have like a line of best fit that goes through all the data points. Okay. And then there's one last thing that's a little subtle. Since each of these data points, these blue data points, right, they represent several measurements. Typically they're like an average of many different measurements. So there's some error, right, associated with those measurements. And typically you will represent that error. Some graphs or some people will use like error bars to represent, plus or minus one standard deviation, I guess, would be one example. So you represent the fact that there's some variability, right, some error there. Another way is qualitatively, you could just circle the data points just to show that there's some error qualitatively. We don't know exactly what that measurement is, but there's some error that there's qualitative error. For this class, you don't have to really worry about that too much. When you do your graphs on the computer, you don't have to circle the data points or anything like that, but you should be familiar with that in general, each of those data points has some error associated with it. Okay, so if we go to the second page, this is an example of a graph that's drawn better, right? It has labels with units. So in this case, it would be angle in degrees is the X variable, right? Or the independent variable. And then the dependent variable on the Y-axis is range, and the units are centimeters. So then for the title, you could just say range versus angle. And I put range of a projectile versus angle of projection. And notice here that there's a smooth curve that goes to the data points, right? It's like a least squares smooth curve. In fact, in this case, it's like a sine wave that goes through all the data points. That's the red curve. And then I circled each data point to show qualitatively that there's some error associated with each data point. You don't necessarily have to do that. The thing that's going to be important, the things that are going to be important for you guys is that you have labels with units, a title, and in some curve of best fit. Typically, it'll be like a line of best fit or maybe a quadratic, like a parabola, things like that. Okay, on the next page, this is just a quick review on how to calculate slope. This may come up, especially if you're doing a graph by hand. If you do the graph on the computer, which most of the graphs will be done on the computer using something called Pascal Capstone, when you do a line of best fit, it'll give you the slope. It'll give you that information. But let's say you were asked to do a graph by hand and you're asked to calculate the slope of the line of best fit. So here's an example. Let's say I'm plotting velocity, which is in meters per second, versus time in seconds. So the blue data points are my data. It's pretty linear, right? So I'm going to do a line of best fit. So the red line is a least squares fit through all that data. And now I want to calculate the slope of that line. So the one thing that you don't want to do when you calculate the slope is you don't want to just use two of your original data points. What you want to do is you want to do the line of best fit first, and then pick 2 points on that line. So in this case, right here, I chose this point where this X is, where I have 5, right? So 5 seconds is my X variable, my independent variable, which is time in this case. And then comma 14, 14 is my dependent variable, right? That's the velocity. So 5 comma 14. Then I chose this point here. So 15 would be the time, 15 seconds, and then 34 would be the velocity, 34 meters per second. And now how do I calculate the slope once I have those 2 points? Well, that's simply going to be rise over run, right? It'll be, you can think of it as velocity 2, 34, minus velocity 1. So that's where I get the change in velocity. Delta V is 20, 34 minus 14 is 20, divided by the change in the horizontal variable, which is time. So this is like T2 minus T1. So 15 minus 5 is 10, right? That would be my change in time. And then the change in the velocity divided by change in time, that's like rise divided by run, that would be 2. So the slope in this case would be 2. And it has units of meters per second, which we write as meters per second squared. So the slope in this example is 2 meters per second squared. Okay, and actually it turns out that's going to be the constant velocity of this object, the velocity of this motion. So if you have velocity versus time and you have a linear fit, then that slope is the acceleration, and it ends up being constant in this case. So 2 meters per second would be the acceleration. Again, the important thing was make sure you pick 2 points on the line of best fit if you're going to calculate a slope by hand. Okay, on the next page, this is going to be really important for the lab sections that are going to look at the relationship of the period of a pendulum versus the length of a pendulum, right? So this is basically physics 207 and 212 will definitely be doing this part of the lab. 206 is not responsible for this. So if you're in physics 206, you don't have to worry about this particular part. So when you do this experiment, right, looking at, again, the relationship between the period of a pendulum and its length, one of the questions that you're going to be asked in the lab manual is to come up with an equation that gives the period as a function of the length of the pendulum. So let me kind of walk you through that and show you how to do that. So you're going to be doing 2 graphs. You're going to be plotting the period versus the length of the pendulum, and you're going to be plotting the period squared versus the length. You're basically going to square the period values that you get versus the length of a pendulum. Now, what does the period mean? It's basically the time for one oscillation. If you have a simple pendulum and you let it oscillate, the time it takes for one oscillation would be the period. Actually, let me show you that in a simulation here. You're either going to be doing this lab using a physical pendulum, like a wooden pendulum, or using a simulation, or both. Actually, if you're in 212, I'm gonna have you do both of these. But let me show you what this looks like in the simulation. Okay, so here's a simulation of a simple pendulum. It basically consists of a string, or it could be like a lightweight rod, and you have a mass that's at the end of the string. So basically all the mass is considered to be at the end. And you would displace this by a small angle, usually like maybe 20 degrees would be fine. And then you release it and it oscillates back and forth. So the period of the pendulum is the time for one oscillation. So if I release it from here, the time it takes to go to the other side and then back, that time would be the period. So the time for one complete oscillation. So what we want to look at in this lab is we want to look at the relationship between the period and the length. So if I adjust the length of this, if I make it smaller or longer, how does the length affect that period? Okay, so that's really what we're looking at. Okay, so one of the things that you're going to be plotting is you're going to be doing a graph of the period squared versus length. So once you find those period values, you're going to square them, and that's going to be on the y-axis, right, your dependent variable, and the length of the pendulum will be on the x-axis, horizontal axis. And what you're going to find when you plot period squared versus length is that you get this nice linear fit to the data, right? So you have a line of best fit through the data. Okay, now remember, the question that you're ultimately going to be asked is you want to come up with an equation that gives the period as a function of the length. Okay, and we're gonna figure it out by knowing that the period squared versus length is linear. So actually, let me jump over on the iPad to show you this. Okay, so again, what do we know? We know that when we plot period squared versus length, we get a linear fit, right? It's a linear equation. Now, what's the equation of a line? Well, there's many ways of writing it. The one that you guys are probably most familiar with is the slope-intercept form, right? Y equals mx plus b. So let's just start with that. We'll start with y equals mx plus b. Now, if you noticed, right, in that particular graph, what was the y variable? What was plotted on the y-axis? That was period squared, okay? So usually, period we denote by T, capital T. So this is period. And the y variable was period squared. So in place of y, I'm going to write T squared. What was the x variable? Well, what was plotted on the x-axis? If you remember, it was, if you look at the handout right now, it's the length of the pendulum, right? So I'm going to call L the length. So this is the length of the pendulum. This is really going to be like in centimeters, and this was in seconds, right? Period in seconds, it's a time, and length is a distance. So we're going to use centimeters for this part. The m is the slope, right? So I'll just leave that now as m, slope. X, again, we're going to call the length of the pendulum that was plotted on the horizontal axis. And then the b in this case, well, what is it in general? It's the y-intercept, right? It's where the line will pass through the y-axis. But if you notice on that graph, it basically goes right through the origin. So we're going to assume that b is 0. So we're going to assume that this is 0, okay? So we have our equation, T squared equals m times L. So actually, we're almost there, right? Remember, this question is going to ask for the period as a function of the length. Right now, we have period squared. Well, how do we get the period if we have period squared? I can simply take the square root. I can take the square root of both sides, right? So let's do that. If I take the square root here, square root of T squared is going to be T. It's really plus or minus T, but we want the positive square root in this case. And then For the right-hand side, I can write this as the square root of m times the square root of L. Remember, if you have the square root of a times b, if you remember from algebra, you can split this up into the square root of a times the square root of b, right? As long as they're both positive. Okay, so we're almost there, right? We have period now, and it's an equation in terms of the length. But there's one more thing I know. I also know the m, right? Remember, the m is the slope of the period squared versus length graph. This is the slope, right? And if the original graph was period squared versus length, it's the slope of that particular graph. So if you look on that handout again, you're going to see that that slope, if you calculate it, it's around 0.04, right? Actually, let me go back to that. So here, again, you don't have to worry about this. When you do this graph of period squared versus length, you're going to do a linear fit and it'll give you the slope value. Here, just for practice, I did it by hand. So I chose a point here, 20, 0.8. I chose a point here, 40, right, which is my length, and 1.6 is my period squared value. And then if I do 1.6 minus 0.8, so that changes 0.8, that's like my rise. And then my run is 40 minus 20, which is 20. And if you do 0.8 divided by 20, that's where you get the 0.04. So the slope of this is really 0.04, and it has units of seconds squared over centimeters. Okay, so that's where the slope comes from. Again, the computer will give you the value, but you could calculate it by hand if you need to. Okay, so now we can actually plug in that value, right? So I know that my slope was 0.04, and you guys will be able to plug in your particular value when you do the fit, when you do the linear fit to that graph, times the square root of L, right? The L is one of our variables, the T is our other variable. And then I can simplify square root of 0.04 is 0.2. So really I can write this as T equals 0.2 times square root of L. And that's my answer. That's what I was looking for. That gives me an equation that gives the period as a function of the length, right? In terms of the length. You can even think of this in functional form. You could write T is a function of the length, right? It's equal to 0.02 times square root of L. Okay, so you're going to be doing something very similar. And actually what you should find is that you get a value that's very close to 0.04. It may not be exactly the same, but it should be very close to that. So you're going to have T equals some value. It'll be something probably pretty close to 0.2, but it depends on your data. So it may not be exactly the same, times square root of L. And that will be the correct equation that gives the period as a function of the length. Okay, the next thing I want to talk about is the difference between accuracy and precision. So we're going to also develop measurements to measure the accuracy of an experiment and precision. So accuracy is defined to be the degree of closeness of measures of a quantity to the true value of that quantity. So it's when you compare like an average of your experimental values to a true value or an accepted value, or sometimes we'll say predicted value, right? So you're comparing your average that you got, your experimental value, to a true value. So in this class, the accuracy is going to be measured by something called the percent experimental error. Okay, and I'll show you how to compute that in a little bit. So percent experimental error, that's going to be important. You're going to be computing it over and over and over again throughout the course. Next definition, precision. So precision is the degree to which repeated measurements show the same results. And in this class, precision is measured using something called the relative average absolute deviation. It's kind of like a standard deviation if you're familiar with statistics, except you use absolute value instead of squaring them, right? So it's called the relative average absolute deviation. Now here's the confusing part. The lab manual, which was originally written like in the early 70s, the first edition, It has sort of some older terminology there. And it refers to this measurement, the relative average absolute deviation, as the percent experimental accuracy. And we're kind of stuck with that, that terminology. So it's called percent experimental accuracy, but it's not really a measure of accuracy. It's a measure of precision, right? It's a measure of the variability. So it's a little unfortunate. Hopefully, I think just terminology changes over the years. So at some point, we're going to need to change that in the lab manual. But even though it's still called percent experimental accuracy, it's really a measure of the variability, a measure of the precision. Okay, and it's really this measurement, relative average absolute deviation. It's the same. It's what we're calling percent experimental accuracy. So we're kind of stuck with that terminology. And then resolution is the finest to which a measuring instrument can be read. Basically, it's like how many decimal points you can read a particular instrument, whether it's a vernier caliper, which measures distances, which we'll talk about later in this lab. It could be like a scale that measures masses, right? So how many decimal points? Can we read it to 2 decimal places, 3 decimal places? That sort of gives you the resolution of the instrument. So to give you an idea of the difference between accuracy and precision, this sort of target bullseye example is typically used. So in this first case, right, this upper left-hand case, here are your data points. So these are your measurements, right? So there's like 7 different measurements. And notice that if you were to average these, it's probably going to be like here somewhere, right? It's going to be outside of the center. So that's why it's low accuracy, because the average of these is not in the center. So it's low accuracy. This also represents low precision. Why? Because all the values are like spread out, right? There's a lot of variability here. They're not clustered together. So that would mean low precision. To the right here, definitely it's low accuracy, right? Because the average would be out here somewhere when the true value is right in the center. So the true value is considered to be in the center of the bullseye. So that's low accuracy. But this is an example of high precision because all those values are almost the same, right? They're clustered together. So there's little variability in the measurement. So it's high precision. This would be an example of high accuracy because basically the average is pretty much in the center near the bullseye. But it's low precision because there's still some variability, right? They're still spread out. And this is sort of like the best case, right? Where we have high accuracy, the average is right in the center, and they're all clustered together. So there's low variability, so there's high precision. So this is both high accuracy and high precision. Okay, so now I want to show you how to measure these things. How do we measure accuracy? How do we measure precision? I'm going to start with precision. So a measurement of precision. And this, because this is the sort of longer, a little more complicated one to do. And again, what we're going to learn, what we're going to compute is something called the relative average absolute deviation, which in our lab manual is called percent experimental accuracy, even though it's really a measure of precision, right? It's a measure of variability. So let's talk about that. How do we calculate this percent experimental accuracy? Because again, this is something you'll be asked to do over and over and over and over again throughout many of the labs in this semester. Okay, so here's the example. I have some rectangular object, right? Think of it as a rectangular board, maybe, right? Some piece of wood. And let's say I measure the length 10 times and I measure the width 10 times. And I want so since I did 10 measurements, right, they're not all the same. There's some variability here. I want to get a measure of that variability. Well, so basically we're measuring precision, right? And that's when we're going to compute the percent experimental accuracy to measure that precision. So how do I do that? How do I calculate? Let's start with length. Let's see how to calculate the percent experimental accuracy for the length here. So actually, I'm going to do this on the iPad to show you this slowly. Let me write down these 10 values here of the length. So, and then I'll show you the iPad in a minute. So I have 8.2, 8.1, 8.0, 8.2, 8.3, 8.1, 7.9, 8.0, and then 8.4, 8.2. Okay, so let me go to the iPad. Okay, so these are my 10 values, right, of the length. So these are my lengths. And they're in centimeters. Now, the first thing you should notice is that if you look at each of these values, see how they're all to one decimal place? So this particular instrument, its resolution was 0.1 centimeters, because that's like the smallest length that you can measure with this particular instrument. So the resolution really depends on the number of decimal places. So in this case, the resolution, I'll write it up here, is 0.1 centimeters. Right, so you should always be familiar with the resolution of the instrument, because that'll be important. All right, so how do I compute percent experimental accuracy? Well, the first step is I need to average these 10 values. So if you average these 10 values, you're going to get like 8.14. But what we need to do, let me just double check that and make sure that's correct. Yeah, 8.14. What we need to do is we need to always average that. When we average that value, we need to round it to the resolution of the instrument, which is one decimal place. So really, I'm going to round this to 8.1. So that's my average length, 8.1 centimeters. Next, I need to form a new column. And this new column is what we're going to call the absolute deviations. Which are also in centimeters. And how do I compute those? Well, those basically represent how far each data point, so like the first data point is 8.2, how far each data point is away from the mean, right? Away from this average. So the way that you compute that is you take each data point, you subtract the average, and then you take the absolute value of it, right? It's an absolute a deviation means like a difference, right? So it's an absolute value of the difference between each data point and the average. So in this case, right, this would be the absolute value of 0.1, which is equal to 0.1, right? Positive 0.1. Then the next one, I'll do a few of these. This would be 8.1 minus 8.1. Well, that's absolute value of 0. That's just 0. Then it would be 8.0 minus 8.1. That's going to be negative 0.1, but I want absolute value of that, right? Negative 0.1. So that's going to be positive 0.1, right? When you do the absolute value. And so on and so forth. And many times you don't even need to do all the math out. You can sort of just do this in your head. You can say, how far is each data value from the mean? So like the next one would be 0.1, right? It's 0.1 centimeters away. Then 8.3 from 8.1, that would be 0.2. 8.1 from 8.1 is 0 again. Then 7.9 from 8.1, that was 0.2. Right? It's minus, but you take an absolute value, so it's positive 0.2. Then you're going to get 0.1, and then 0.3, and then 0.1. Right? Those are all my absolute deviations. Okay, now what? So now what I want to do is I want to average those absolute deviations. If you average these, you're going to find that you're going to get 0.12, right? So if you add these up and divide by 10, you're going to get 0.12. But then you want to round again to the resolution of the instrument, which is one decimal place. So this is going to be 0.1. So this right here, this is what's called the average absolute deviation. All right, so we're almost there. Remember, our goal is to compute the percent experimental accuracy, which is a measure of the precision, right, of the variability. So last step. So to actually calculate the percent experimental accuracy for length in this case, what I do is I take my average absolute deviation, which is 0.1, and I divide by my length, my average length, so 8.1, and then multiply by 100 just makes it a percent. So multiply by 100 to make it a percent. And in this case, I'm going to get 1.2%. So that would be my percent experimental accuracy for length. And the lower, the better, right? It means that there's less variability. If I have a lower percentage, it means I have less variability. The numbers, the values are closer together, right? Those 10 values are fairly close together. So I have higher precision, right? If I have a lower percentage. Okay, so now you can do the same thing with the width. So let me go back to that handout for a second. So I would average the 10 width values, round to the resolution of the instrument, round to one place. I'm going to get 3.2. Find all my absolute deviations. Remember how far each value is away from the mean. So 0.1, 0.1, 0, 0, etc. Then I average these absolute deviations. I get 0.1. Right? Make sure you round to the resolution of the instrument, which is one decimal place, so 0.1. And finally, if I want the percent experimental accuracy in width, I would take the 0.1, divide by my average width times 100. In this case, I get 3.1%. Okay, so now we know the percent experimental accuracy in length is 1.2%, and the percent experimental accuracy in width is 3.1%. Okay, well, another thing that you might want to do is you might want to calculate the area, right, of this rectangular, let's say it's a board, this rectangular board. So how do we find the area of a rectangle? Well, that's simply going to be length times width, right? So to actually find the area of, I call it a plate here, rectangular plate, you're going to take the length of the plate or board times the width. So all you're going to do is plug in your average length times your average width, right? And that will give you the area. So in this example, I have 8.1 centimeters times 3.2 centimeters, and I get 26 centimeters squared. I'm just multiplying these. And in this example, actually was being very careful with significant figures as well, right? So since I have two significant figures for the length, two significant figures for the width, the answer can have at most two significant figures. So I just have two, right? 26. Now, there's one other thing you might want to do. We know the area now, right? We found it by length times width. What if we want to find the percent experimental accuracy for the area? So this is like a variable that consists of, right? It basically comes in this formula. It comes from multiplying length times width. So how do I find the percent experimental accuracy for the area if I already know the percent experimental accuracy for length and the percent experimental accuracy for width? How do I calculate the percent experimental accuracy for the area? And I know the formula for area involves length times width. So basically, like, how do those errors propagate? How do you, what do you do with those percent accuracies to get the correct percent experimental accuracy for area? Well, the rule is, and you're going to see this rule over and over and over again, if you have an equation that involves multiplying variables. So in this case, I have area as length times width. So actually, either if the variables are multiplied or divided, in both cases, the same rule is going to apply. If you want to find the percent experimental accuracy for the dependent variable for the area here, what you do is you add the respective percent experimental accuracies for length and width, right? If you multiply or divide those variables, you always are going to add the percent experimental accuracies. So for example, in this case, we know the accuracy for length was 1.2%. We know the accuracy for width was 3.1%. Since area involves multiplying length times width, if I want to find the percent experimental accuracy for area, I simply add the percent experimental accuracy for length plus the percent experimental accuracy for width. So it would be 1.2% plus 3.1%. That gives me 4.3%. So that would be the accuracy for the area of this rectangular object, right? And that's always going to be the case. Whenever you have a formula that involves multiplying or dividing variables, and you want to find the percent experimental accuracy of this dependent variable, you have to add the respective percent experimental accuracies. Okay, so hopefully that made sense, and you'll get a lot of practice in this first lab that we have to do in how to calculate percent experimental accuracies. But you can review this example again, maybe do it on your own to make sure that you're getting exactly the same answers as me. Okay, the other thing that you're going to calculate throughout the entire semester, many of these labs, is the percent experimental error. Now, this is a measure of the accuracy. I know it's confusing the way the terminology is, but this is when you want to compare an experimental value to an accepted gold standard predicted value. Okay, so let's say one of the things you're going to be doing in the first lab is measuring the density of this small aluminum cylinder. Let's say that you did the experiment and you found that your experimental value for the density was 2.6 grams per centimeters cubed. Okay. Then you look this up on the internet or in a handbook, and you find that the accepted value or predicted or gold standard, I kind of use all those words interchangeably. So the accepted value for the density of aluminum is 2.7 grams per centimeters cubed. So now we want to compare your value, your experimental value, to the gold standard. How do you do that? That's when you compute this percent experimental error. So, and it's very simple. All you have to do is the following. So to find the percent experimental error, in the numerator, you're going to have the absolute value of the experimental value minus the predicted or accepted value, right? So you're just taking the difference, but then you're making it positive by taking the absolute value. And then in the denominator, you're always going to have the accepted predicted gold standard value. Okay, and then times 100 just makes it a percent. So for example, in this case, right, it would be 2.6 minus 2.7, but then when I do absolute value, that gives me just positive 0.1. I divide by 2.7 and then times 100, I'm going to get 3.7%. So that's my percent experimental error. And again, the lower, the better, right? Lower percent error means that your experimental value was closer to the accepted value. So the lower the percent error, the better. Now, there is one subtlety here. It turns out that for percent experimental error, which we were just talking about, it is okay to get 0%. That means that your experimental value was exactly the same as the accepted predicted gold standard value. But when you calculate percent experimental accuracy, which we did earlier, right, when we're looking at the table, measure the variability, right, measure precision. When you're calculating accuracy, it turns out you can never have an answer of 0%. So let me show you how you would handle that case if you were to get 0%, like what you should do. Because for accuracy, you can't end up with an answer of 0%. For error, it's okay, but accuracy, it can't be, because we always assume that there's some like error with the instrument itself or when making the measurement. So that's why accuracy can never be 0%. So how do you handle something like that if you're going to get 0%? Let me show you that on the iPad. Okay, so let's assume that you collected some data. Actually, let me just use the example that we're going to actually do in lab where we calculate the density of a small aluminum cylinder. So one of the things you have to do is measure the height and diameter of that cylinder. So let's say you measure the height 5 times. Right? So here's the height in centimeters. And let's say these are your 5 values: 5.32, 5.32, 5.33, 5.32, 5.32. Okay, so first, what's the resolution of this instrument? You're going to use something called a vernier caliper. Well, just by looking at those values, see how they're all to 2 decimal places? So the smallest that this vernier caliper could measure is 0.01 centimeters, right? So the resolution of this instrument is 0.01 centimeters. Now, if we want to compute the percent experimental accuracy, right? Remember, it's a measure of precision, to measure the variability. The first step was to find the average, right, of these 5 values. So if you add these up and divide by 5, you're going to get 5.3, I guess it'd be 322. But remember, you have to always round to the resolution of the instrument, which is the number of decimal places. So you want to round to 2 decimal places. So if I round that, I'm going to get 5.32. Right? So that's my average height in centimeters. Next, we form that second column of the absolute deviations. Absolute deviations. Also in centimeters. And remember, that's how far each value, each data value is away from the average, right? Away from the mean. So in this case, remember, you could do it mathematically. So you could take each value, subtract the mean, and then take the absolute value of that. In this case, it's going to be 0.00, right? Second one will also be 0.00. But notice the next one is going to be 0.01. Then 0.00, then 0.00. The next step was to average all those absolute deviations. So if I average these, I'm going to get 0.002. But then I have to round to the resolution of the instrument. That's always important. Remember, in this case, it's 2 decimal places again. So if I average these, I'm going to get 0.00. Now, if we try to compute the percent experimental accuracy, normally what I would do is I would take this average absolute, oops, the wrong one here. I would take this average absolute deviation divided by my average height times 100. But if I do that in this case, I'm going to get 0%, right? Because 0 divided by 5.32 is 0 times 100, which is 0. And we just argued earlier that for when we're calculating percent experimental accuracy, measure the precision variability, we can never get 0%. So what do I do in a case like this if I'm going to get 0%? Well, the problem is this average absolute deviation. This value always has to be at least the resolution of the instrument. So when you go through the work and you average this, if this happens to be less than the resolution of the instrument, which in this case is 0.01, then you have to default to the resolution of the instrument. So in this case, we have to use 0.01 as our average absolute deviation. And notice that this is only going to come up when the values are either the same or really close to one another, where you have an average absolute deviation that turns out to be less than the resolution of the instrument. So therefore, you just use the resolution of the instrument when you're computing the percent accuracy. Okay, does that make, hopefully that made sense. So now I can actually compute it. So percent experimental accuracy for height is now going to be 0.01 divided by 5.32 times 100, and whatever that is. So if you work this out, in this case, it turns out it's like 0.19%. But notice it's no longer 0, right? So again, if you run into that situation, you just have to make sure that this average absolute deviation here is at least the resolution of the instrument. If you get a value that is larger, right? If this is larger than 0.01, then you just use it. Then it means you have more variability. You can have a larger percent experimental accuracy, but that's fine. But it has to be at least the resolution of the instrument. Okay, and then so we're almost done. Here's the last page of this handout. This is just an example where we're actually looking at the density of that small aluminum cylinder. So let's say you went through the experiment and you found the volume of that cylinder to be 5.34 centimeters cubed. And this is your percent experimental accuracy, plus or minus 3.4%, right? So that's the volume. Now, to find, ultimately we want to find the density, right? To find the density of something, well, how do we compute that? Well, it's going to be the mass divided by the volume, right? In fact, the formula is right here. Density is usually represented by the Greek letter rho here. So rho is equal to m mass divided by v volume. So mass divided by volume. Well, in order to do that, we need to find the mass, right? Let's say we already have the volume here. So the V would be 5.34, but we need to find the mass. So what we can do is we can mass our little cylinder on a scale, electronic scale. Let's say that we do that and we have 5 measurements. And notice that this scale, its resolution is 0.1 grams, right? Because it's 1 decimal place. So if I average these, this is going to be my average mass, 13.9, right? I can use that in the formula here. If I want to compute the percent experimental accuracy for this mass, then I have to find all the absolute deviations. So in this case, this is 0, right? 0.0 away. This is also going to be 0. This is 0.1, 0, 0. Now, if you average these, you're going to get 0.02, but then we have to round to 1 decimal place, so it's 0.0. But then we just said we can't use that because otherwise we'd have 0 for a percent accuracy. So we have to use at least the resolution of the instrument, which is 0.1. So then if I take the 0.1 divided by 13.9 times 100, 0.72, that's going to be my percent accuracy for mass. Okay, so in this case, that did come up because the values, we weigh something on a scale, you're pretty much going to get the same values, right? So that's when you're going to have to use this resolution of the instrument here when you compute your percent accuracy. To actually find the density, you're simply going to plug in your average mass and your average volume. If we do that in this case, 13.9 divided by 5.34, we're going to get 2.6 grams per centimeters cubed. So that would be our density, 2.6. Now, if I wanted to find, let's say I wanted to compute, so I know the percent accuracy for mass, 0.72. I know the accuracy for volume. We assumed we did it earlier. We got 3.4%. That's the accuracy for volume, right? This is the volume and plus or minus the percent accuracy. So let's say I want to find the percent accuracy for the density. Well, in this formula, density is equal to mass divided by volume. Remember earlier I said if you have some dependent variable, in this case the density here, and it involves either multiplying variables or dividing. In this case, we're dividing mass divided by volume. Earlier when we did area, it was length times what we're multiplying, but either multiplying or dividing, it's the same rule. Then if you want to find the percent accuracy of this dependent variable, the density here, then you have to add these respective 2% accuracies. So since I'm dividing mass divided by volume, if I want to find the accuracy for density, I have to add the accuracy for mass plus the accuracy for volume. So 0.72, that was the accuracy for mass. 3.4 was the accuracy for volume. If I add those together, I get 4.12%. That's the accuracy for the density. Okay. So if you want to, all you really have to remember for this course is whenever you want to find the percent accuracy for a dependent variable, typically it's going to involve multiplying or dividing variables. You just have to remember you have to add the respective percent accuracies. Okay. Then the other thing we could do is we could compare this value to like a gold standard. Let's say we had a gold standard of 2.7, then you'd have to compute the percent experimental error, right? Comparing your value to the gold standard. Okay, hopefully that was helpful. And that should give you plenty of information to do the first lab. Thank you.